Okay, so this is going to be the second try at the live lecture. It is definitely not as easy to work from home as it is elsewhere. Okay, I'm going to get into chapter 4. We're going to be talking about periodic functions, which all trig functions are. I'm going to go ahead and fill in this first page. So a periodic function is a function f such that f of x is equal to f of the quantity x plus n times p for every real number x in the domain of f, every integer n, and some positive number p. The least possible positive number for p is what's called the period of the function. And the circumference for the unit circle, the circumference of any circle is 2 pi r. For the unit circle, the radius is 1. So the circumference will be 2 pi for your unit circle. And then for the sine and cosine functions, the least value for p is actually going to be 2 pi. Therefore, the sine and cosine functions are periodic. They have a period 2 pi, okay? Now I want to emphasize that that's just for the parent functions. So sine and cosine parent functions. Those parent functions would look like f of x equals sine x, or y equals sine x, and f of x equals cosine x, or y equals cosine x. So eventually, what we're going to be looking at are functions that look like this. You're going to have some value c plus a times whatever your trig function is. Okay. And then you're putting in this quantity, b times x minus d, into the trig function. So like an example of what we're going to be looking at later, f of x equals, what's the one that I wanted to use? So to be familiar, 4 minus 2 sine 3x minus pi. Okay, and we're going to find that we can actually rewrite this function in the terms we have above. I'll get into all this later. Okay, so this is still a sine function, but it's going to be shifted in all kinds of ways, which we'll talk about soon. So when we see the period for our parent functions being 2 pi, for our later functions, the period is actually going to be 2 pi over b. Okay. All right, let me save that. And then I'm going to go ahead and clear this screen. Okay, so remember, for this part here, we have a period of 2 pi. So 2 pi is going to go in here. Okay. So just a quick little example of what's being said. We'll just look at the sine one. Okay. So suppose x is equal to 0, and this is going to be in radians. Okay. Then what we're saying here is that sine of 0 should be the same thing as sine of 0 plus 2 pi. And that should be the same as sine of 0 plus 2 times 2 pi. And that should be the same as sine of 0 plus 3 times 2 pi, and so on and so forth. Okay, so let's think about this for sine of 0. If we think back to the unit circle, okay, sine of 0, that means we're at 0 radians, that'd be right here. Remember, the point there would be 1, 0. And then this second coordinate would be your sine value. So sine of 0 radians is actually equal to 0. Now let's look at the next one. If we're looking at a sine of 2 pi, hopefully you're seeing that we would be going a full rotation around the circle, and then we would be at 2 pi radians. So we'd actually get the same sine value. Okay, and then this also repeats for sine of 4 pi and sine of 6 pi, and so on and so forth. Okay, so 0. Okay. All right, and then we're going to see that the same thing is going to happen with the cosine function for the same reasons. Let me go ahead and save this, and then we will go ahead and move to the next page. Let me clear this out. Actually, before we move to the next page, let's go down here and just quickly fill this in. So for this, it might help to think about the unit circle again. Okay, so let's put a few points on this circle. We have right here, the point 1, 0. Up top, we have the point 0, 1. We have negative 1, 0. And we have 0, negative 1. Okay, remember for the unit circle, we have cosine S, sine S for our values. So what this is saying is what happens as S increases from. So remember, the way that we measure S is from standard position. This is your initial side. And then you have your terminal side over here. Now, remember, inside there's a central angle, theta, and then for the unit circle, theta is actually equal to this arc length here, S. Okay. So it's saying what happens as S increases from 0 to pi over 2. All right, let's actually do this. Let's write in pi. Oh, you can't see that. So this is when S equals pi over 2, S equals pi, S equals 3 pi over 2, and S equals 0, S equals 2 pi. All right, so as S increases from 0 to pi over 2, for the sine function, look at what happens to the second coordinate here, the y value. We see that we increase from 0 up to 1. Okay, let's keep going with sine first. If we're at pi over 2 and we go up to pi, we see that we decrease from 1 to 0. From pi to 3 pi over 2, we decrease from 0 to negative 1. And finally, from 3 pi over 2 to 2 pi, we increase from -1 to 0. Okay. For cosine, we're looking at the first coordinate, the x value of the point. Cosine first decreases from 1 to 0, and then from 0 to -1, and then from -1, sorry, let me restate that. When we're at pi and we're going to 3 pi over 2 for our radians, the increase is going to be from -1 to 0. And then finally, cosine, we see that we go from 0 to 1. Okay, I'm going to save that, and then I'm going to clear my screen out again. Okay. If anybody has any questions about any of the things that pop up, you can just take a picture of it and we can discuss at the Q&A in a little while. Let me clear these drawings and then let's keep going. So you actually have these charts in your textbook that's available on MML. You can just fill it in there. And if you have any questions about it, you can ask me. So I'll go to draw. Okay, so this is chart and book available on MML, okay? And then same thing for the next page. This chart is going to be available on your textbook, MML. Okay. So before I move on though, I am going to talk a little bit about where this graphing is coming from. So clear my drawings, let's go to the sine function again. So we already saw what sine of 0 should be. So basically for x is going to be what you have for radians. You might see degrees used in your book. You technically can use degrees as well, but I want to kind of get out of doing that. Essentially, radians are the real valued numbers that you'd want to use. So if you are plugging degrees in here, you'd have to realize that that degree would actually be equal to the arc length there. So theta would be equal to x in this case. And then x would still be plugged in radians, come out with a trig function value. But I'll just go ahead and say it's going to be in radians for right now. And then f of x will be your trig function value. Okay, so like for example, let's look at when x is equal to 0. I'm trying to evaluate f at 0 radians. And I know that that's going to be equal to, 1 second. Let me try to color code to the best of my abilities. Okay, so my function value at x equals 0 radians will be given by sine of 0 radians. And we already saw that that comes out to 0. Okay, next bit. Let's try when f is equal, sorry, when x is equal to pi over 6. Okay. Then we're evaluating sine at pi over 6 radians. Okay. Now, hopefully you remember that on the unit circle, that is when your y coordinate would be 1/2. Okay, and so on and so forth. So we're going to have 1/2 here at pi over 4. Sine of pi over 4 is root 2 over 2. And then root 3 over 2 and 1. Okay, so then if you look down here, kind of hard to see, sorry, but the points that you're looking at, there's 0, 0. Pi over 6 would be somewhere over here, and then you would have 1/2. Pi over 4 would be in the middle, that's root 2 over 2. Pi over 3, root 3 over 2. And then at pi over 2, we get 1. Right? Now, sine of pi is 0. Sine of 3 pi over 2 is -1. And sine of 2 pi is 0. Okay. Now, essentially, we're going to be using 5 points when we graph. The 5 points that we would be concerned with in this particular graphing would be the zeros. Okay. And we're also concerned about when we get a function value of 1 and when we get a function value of -1. Okay. So essentially for your sine and cosine graphs, I don't even know why I have an alarm set to 2. Okay. So for sine and cosine graphs, we're going to be looking at actually, let me wait on that part. Let me wait. I'm going to go into our first example first, and I'll start to explain from there. So let me save this, and then let me clear this screen. Okay, let me move down here to our first example. So we get into graphing. There's a few things that I'm going to want to talk to you about first. So I'm going to actually open up a whiteboard for this. Okay, so for sine and cosine graphs, we're going to have y. Remember, y is actually the same thing as f of x. We're going to have c plus a sine quantity b times x minus d, or y equals c plus a cosine b times x minus d, right? Essentially, we are going to need to figure out like what these shifts mean. So a, when you take its absolute value, is what's called the amplitude of your graph. And that's going to be your vertical stretch for the graph. B is going to be your horizontal stretch for the graph. C is going to be your vertical shift. And D is going to be your phase shift. And phase shift is also known as horizontal shift. Okay, so that tells you what's happening to your parent graph. So the amplitude, that's going to be stretching your graph. Your horizontal stretch, that's stretching this way. Vertical shift, that's going to take your entire graph and move it one way or the other. Oh, the vertical, sorry. And then the phase shift or horizontal shift is going to take your entire graph and move it left to right. Okay. So I do want to emphasize, you can kind of tell from the picture, hopefully, but the parts that affect your range are going to be your amplitude and vertical shift. And B and D will affect your domain. Okay. And then one last thing that you're going to need, it's actually going to come from B. So we'll go ahead and put a domain effect here. You're going to need to know what your period is. And for us, the period is going to be 2 pi over B. It's actually going to be for sine, cosine, and the reciprocal functions, but I'm going to wait on the reciprocal functions for right now. Let me save this. And then let me go over the process for graphing before we start one. Okay, so the process for graphing sine and cosine, let me not put a slash so you don't think it's a divide. Okay, so essentially what we're going to be doing, we're going to identify the amplitude, the horizontal stretch factor. Oh, and then actually, just in case, because I don't remember if I said B correctly, and I can't go back since I erased it. B is your horizontal stretch. Okay. All right, so we're going to identify A, B. From B, we're going to get P. We're also going to identify what C and D are. Then we're going to find the n values for X. And in order to do that, we're going to put whatever B times X minus D is between 0 and 2 pi. That would be the start of a period, the end of a period. And then we see how it shifts based on, we see how the B and D values influence our domain, okay? Third, input. For the third part, we're going to find 3 additional middle x values. And then we're going to get 5 x values from there. So we're going to have our endpoint, low end. We're going to have the middle 1, middle 2, middle 3, and then the end value on the high end. Okay. And then from there, we're going to find our 5 corresponding y values. Okay, so we're going to be plugging whatever the x value is here into our function f of x, and then we're going to get some value here. Come on, phone. Jeez. Sorry, let me make sure all the rest of my alarms are off. Okay, there we go. All right, so we're going to find the first y value. Plug in middle x1, second, and so on and so forth. Okay, and then the final step is going to be to graph our points. Okay, and then we will find that we get a nice curve out of this. I want to emphasize that this is graphing the function over one period, which is all you'll be required to do for your exams and things. We save this and then clear it out. Okay, so instead of going back to that classroom example right now, let me just bring it up here. This is section 4.1, classroom example number 1. Okay, so we have graph y equals 1/2 sine x and compare to y equals sine x. Okay, so we're just going to do this over one period. I'm going to make our parent function in blue, and I'll make our shifted function in pink or magenta, whatever color that is. Okay, so we have already seen how to graph the sine function, the parent one. So let's go into our process. Okay, so we see that we have y equals 1/2 sine x. Essentially, you're comparing the form. So y equals c plus a sine b times x minus d. Okay, so from here, what we find, the amplitude is the part that you see right in front of your trig function, okay, when you take the absolute value. So the amplitude in this case is actually going to be 1/2. Now your b value, notice that in this particular format, If we were to expand this, it would be b times x minus b times d, right? Essentially, b, there has to be something there. It can't just be 0 in order for you to see this part here. So if you see an x here, that's really like 1 times x minus 0. When you distribute it out, you'd only get x. Okay, so what that means is that b is 1 and that d is 0. Okay. From b, you can actually go ahead and find your period. The period is going to be 2 pi over b. And in this case, that means the period is 2 pi over 1. So it's just 2 pi. And then the c value, it's whatever's added to your trig function, the sine function. You don't see anything added in front of the 1/2, and you don't see anything added after the x part. So c is going to be 0. Okay, so that's the first part. Second part, we are going to find the n values for x. Remember, for that part, we're going to want to put b times x minus d between 0 and 2 pi. You do not have to write it in this format, though. Okay. Whatever part you see after the sign, that is your b times x minus d. Okay. We don't need to do anything to isolate x here. So what that tells us is this is going to be our low n value. And this is going to be our high n value. Okay. The third part, find middle values. So in order to do that, you're going to take averages. So let's go ahead and do this over here. We're going to have 5 points. We're going to have 0 and 2 pi at the ends. So let's take the average between 0 and 2 pi. So 0 plus 2 pi divided by 2 would be the average. That gives us pi. The average of the n values goes in the middle. Let's take the average between 0 and pi. That gives us pi over 2. Pi over 2 will go between 0 and pi. And let's take the average between pi and 2 pi. That gives us 3 pi over 2. And that completes step 3. We have our 5x values that we need to plot. Let me save this. And then let me get rid of my third step and my second step. Actually, I'm going to just clear this whole thing. Okay. So step 4 is to find our corresponding y values. So you can do this traditionally, but when you practice enough, you're going to see a pattern to this. Essentially, these 5 values are going to be your zeros, your max and your min values for y. Okay, so let's do this in the, these will be your, oh crap. No, what is going on here? Stop. Okay. These will be your zeros, max, min values for y. Okay. So traditionally though, if you're wondering how you would do this, remember you have a function here and you have x values. So you're going to plug those in. When x equals 0, y equals 1/2 times sine of 0. That's 1/2 times 0. So y will be 0 here. Okay. When x is equal to pi over 2, we have y equals 1/2 sine of pi over 2. That's 1/2 times 1. So it comes out to 1/2 for y. When x is equal to pi, we have y equals 1/2 times sine of pi. Sine of pi is 0. So y is equal to 0. X is 3 pi over 2. Y equals 1/2 times sine of 3 pi over 2. And then sine of 3 pi over 2 is -1. So we'd get -1/2 here. And you can probably guess by plugging in 2 pi, we're going to get 0 again. Okay. And then that will take us to step 5, which is graphing points x, y. Okay. Now, if we had have done this, let me go ahead and emphasize that this is for the non-parent graph. If we had have done the same process with our parent graph here, we would have gotten the same x values in this case, but our y values would be just a little bit different. The amplitude for our parent graph is 1. You can't see anything there, right? But there's a 1 here. So wherever you have a 1/2, change those 1/2s to 1s. And the zeros stay the same. Okay. All right, let me save that. And then let me clear this out. And then because it's going to be really difficult for me to graph this and using this pen, I'm going to first see how this works. Let me go ahead and go back here. But I'm going to show you guys Desmos in a minute in order to have it be a bit more clear. So just want to emphasize that our points for this particular graph were 0, 0, pi over 2, 1/2, pi, 0, 3 pi over 2, -1/2, and 2 pi, 0. Want to emphasize that the points for the parent over here are 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, -1, and 2 pi, 0. So 0 would be here and 2 pi is somewhere out here. I'd say a really good method is if you know, like, so this is going to be the low end value and the high end value, to make your 5 points nice and smoothly, put a tick right in the middle of those two, and then put a tick in the middle. Okay. So right here is pi, and so on and so forth. So let's see if we can graph our parent kind of smoothly, and then we'll compare it with Desmos. So you have a 0, 0. Let me actually add, for the y values, we're going to need 1 and -1. And I'm going to put a little half tick in there. That's going to be our 1/2 and -1/2, respectively. So back to parent, 0, 0. Pi over 2, 1. Pi, 0. 3 pi over 2, -1. And 2 pi, 0. Okay, we're going to have a curve that looks like this. Okay, yeah, I can already tell this is not going to work well. So, oh my gosh, that is so ugly. I'm totally going to clear this out when we look at Desmos, but that's kind of the best I can do right now. Let me see if there's any. Oh, hold. Undo. Erase this plate. I think I found a sine thingy. Okay, I did not, but it does look a tiny bit better. Okay, now let's graph the shifted version of the parent. 0, 0. Oops. It's right here. We have pi over 2, 1/2 right here. Pi 0 right here. 3 pi over 2, -1/2. And 2 pi 0. Okay, so for that particular curve, it looks something like that. Okay, emphasizing that this is over one period. Okay. They save that. I just want to emphasize that that process we just went over on the whiteboard, that's the same process you're going to be using for your cosine graphs. Emphasizing, like, until you're comfortable, don't try to learn any crazy tricks or anything. Make sure to actually plug in. So when I get my x values, plug them in to find out what y is, and then you make your curve. Okay. Let me clear these out, and then let me pull up Desmos. Let's see, where is it? Here's. Okay, so let me clear these functions. I'm going to pull up y equals, I guess you don't actually need to write in y for this. So sine of x, that's in purple. And then we're going to put in sine, 1/2 times sine x. And then I'm going to put this between 0 and 2 pi. And I'm going to make this step pi over 2. For the for the min y value, I'm going to put -1, and I'm going to put +1. So that's how it should have come out, okay? This is the parent graph here, 0, 0, pi over 2, 1, and so on and so forth. And then here is the graph that is shifted. So 0, 0, pi over 2, 1/2, and so on and so forth. Okay, there is, do I want to go over the other ones with you yet? Yes. Okay, let me go back really quickly. Almost done here. Let's go to the whiteboard again. So for this part, for cosecant and secant graphs, you're actually going to do a very, very similar process. So you're going to have y equals c plus a cosecant quantity b times x minus d, or y equals c plus a secant b times x minus d. You are essentially going to go about graphing the same way that you do for sine. Or cosine respectively. Okay, but what we're gonna find is that the graphs are going to be a little bit easier to graph than like the tangent and cotangent ones if you just remember some details. So for one, I just want to mention that now this is no longer called the amplitude, just because we're going to find that cosecant and secant graphs have no max and min range values. Okay, but essentially everything else is going to be relatively the same. So here's what I want to do. I'm just going to add on some stuff to classroom example 1 here. Let me save this and then let me clear it all out. So remember we had a y equals 1/2 sine x to graph y equals one half cosecant x over 1 period. This will be our process. So still find your a value with absolute value, but we're not going to call it amplitude. Find your b value. Your period is actually the same. C is 0, D is 0. 2, remember we still have our B times X minus D part here, but want to emphasize that now we have no equal sign. If you forget that, don't worry about it. You'll see how it won't really matter in the end anyway. So, right. 3, find your X values the same way that you did before. Averages. Okay. 4, finding the Y values. Okay. Want to emphasize this. Remember, for y equals 1/2 sine x, we got the values 0, 1/2, 0, -1/2, and 0. So what happens for the graph of y equals 1/2 cosecant x? Okay, the shortcut way, wherever you have a 0 for y, since these are reciprocal functions, this is going to be undefined. Okay, and then these values will be exactly the same. Okay, the reason why, remember, y is 1/2 cosecant x. That's the same thing as 1/2 times 1 over sine x. So let's say that x is 0. If I plug in 1/2 cosecant of 0, that's the same as 1/2 times 1 over sine of 0. And we know that sine of 0 is 0. Okay. Let me save that. Similarly, if x is equal to pi over 2, we would have y equals 1/2 cosecant pi over 2. That's the same thing as 1/2 times 1 over sine of pi over 2. That's 1/2. We know that sine of pi over 2 is 1, so we get the same value. Let me save this. And then let me go to Desmos. Okay. On the same plot, I'm going to plot 1/2 cosecant x. Okay. So remember, we wound up doing that one in green. We should have had 0 undefined. When that's the case, that means there's a vertical asymptote at the given x value. We also had pi over 2, 1/2, which is right here. We have pi undefined. Let me make the vertical asymptote here. Ugly, it should be straight down x equals pi. There should also be one at x equals 0. We had a 3 pi over 2, -1/2, which is right here. And then we had 2 pi undefined, which is an asymptote right here at 2 pi. Okay, so once you make your general sine or cosine curve, the easy way to plot the reciprocal graphs, wherever there's a max, it now becomes a min for your reciprocal function. Okay, min for sine. That's going to be a max for cosecant. Max for sine. That's going to be a min for cosecant. And anywhere you have zeros for sine, you have vertical asymptotes for cosecant. Okay, so I am going to actually stop it here. I will give some more information about this section on Wednesday. I will go over what happens when you have C and D not equal to 0. And I will also talk to you guys about how to graph tangent and cotangent functions. Okay, let me go ahead and stop recording. Hold on a second.